Okay, welcome to yet another session of Introduction to Photonics. During the last couple of sessions, we've been trying to get into this learning outcome of identifying the fundamental principles of photon optics and quantifying photon properties. And to understand that, it was essential that we introduce light as electromagnetic waves. So, if I go back and look at where we started this all, ray optics, wave optics, and last couple of lectures we've been looking at light propagation as electromagnetic waves. Now, what we will do for today's session is actually consider light to be propagating as particles, okay, these quantized electromagnetic waves that are known as photons. Okay, so let's try to see what this is all about. The basis for a lot of this discussion came about when Max Planck was conducting his research. That was to solve this problem of black body radiation. When I say black body radiation, what comes to your mind? What is black body radiation? Can you give any example of black body radiation? Huh? The black holes, more simply, the light from the stars, the closest star that we have, sun. So, when we are looking at sun's radiation, we can consider that as black body radiation. So, Planck was actually looking at black body radiation, and around 1900, when he was trying to explain black body radiation, he figured that light must be emitted as, or this black body radiation must be coming out as quantized electromagnetic waves. So, essentially he was figuring that light is emitted when an atom, or more specifically an electron, actually jumps from a higher energy level to a lower energy level. When that happens, he said, you have this quantized electromagnetic wave packets that are emitted. Okay. So, this electromagnetic wave packet is said is one of those fundamental explanation for how we view black body radiation. So, as you know, black body radiation is something that could be spread over a spectrum, right, and one of the simplest things of explaining that is by considering an hot object. So, when an object is heated to very high temperatures, it could emit light. Where do we use this principle? For our lamps, incandescent lamps, the light bulbs, we don't see those light bulbs anymore. It used to be like a tungsten filament that's, when you pass current through that, it gets really hot. And when you heat it up, we know that we can get light, right, from that. So, to explain some of those things, Planck actually came up with this suggestion that this emission is actually quantized, right. So, quantized wave packets, and Einstein followed it up, right. So, he is actually trying to piece together another puzzle which was quite it was attracting a lot of attention at that time. Einstein was trying to explain photoelectric emission, right. So, what is photoelectric emission? Now, somebody had projected that when light actually falls on some material consisting of all these atoms, molecules, right, and if you have light of a certain kind, right, for example, if you have ultraviolet light, the observation was that with that sort of light you could get electrons emitted from this material. Okay. So, that is what is called photoelectric emission, and so that was an unsolved puzzle at that particular time, and Einstein looked at this and said, and that is quite amazing actually, 1905, it is a really famous year because Einstein came up with these 4 papers which spew out 4 different areas of research. Okay. So, this is one of those for the photoelectric emission, E equal to mc square, that came out of that year. The theory of relativity came out of one of those papers that year, and explanation of Brownian motion was also done in another paper that year. So, 4 papers and decades of research following those papers. So, that's just amazing, right. So, that is why we worship Einstein when we think about scientists. But this was one of those things, and what he basically said was that if this was happening, he pieced together what Planck had already said, it's happening in a quantized manner. So, he said this has to be, light must have quantized energy wave packets with E equal to h nu, where h, quite rightly, he called it as the Planck's constant, because without Planck coming up with that previous observation, he could not have possibly come up with this, and nu corresponds to the frequency of light. Okay. So, now the entire scenario changes quite a bit. Now, so far, I want you to think about this as if you are in around 1900s. All you know about light is that light travels as waves, right, and of course, Maxwell came up with this fantastic observation that light can travel as electromagnetic waves, right, and that is what people knew of, and then Einstein came up and says, no, light actually travels as photons. Okay. So, that was like completely disrupting the entire picture, and then people are really stunned, right, and they are wondering, this guy is pulling a fast one on us, right, this cannot be true, can it explain this, can it explain that, and so on, right. So many of those questions were raised, and as we know now, most of those questions have been answered, and this hypothesis at that time is now something that we consider as a real thing. But just to illustrate one of those, answering one of those questions, let us go back and look at this video. Okay. Let us observe this video for a while, and then we will go back and replay that and try to see this in a little more detail. Let us see this video. So, So first we are considering a particle. We're not telling what sort of particle it is. It's just some small balls that are bouncing around, and they bounce around this interface, and then you saw that picture, what it creates, and now it's a wave, right? And this is the, you can say, is the Young's double slit experiment. We know what's supposed to happen, right? So it's supposed to create these interference fringes. And now we are looking at a quantized object. So it can be looked upon as a particle, but it has wave-like properties, right? So when you observe, it's a particle, but this particle actually is exhibiting wave-like properties. So let's go back and look at that once more. So when you observe, that's the observation screen, you observe it as a particle, but if you have multiple observations, quite interestingly, all these particles start making a pattern. It's a fairly well defined pattern, just as the case of the wave. Okay. So what else, what exactly is happening? If I go back and look at this picture, right, it's emitted as a quantum particle, okay, but see how it's, that quantum particle has got a certain wave associated with it. From electromagnetic theory, you can think of this as some electric and magnetic field it's carrying. It's going as an electromagnetic wave, okay. It's a particle, right, but it's got this electromagnetic wave that's associated with this propagation, and because of that, now you are seeing, this interference effects, because when you put a slit, when you put a couple of slits between them, then the secondary wave fronts now start interacting with each other, and then it gives rise to this interference pattern, which actually shows up as bunch of particles falling in different places. Okay. Now this is actually an advanced topic, but just to complete the video, let's go ahead and try to do this. Okay. So what we have here is this person that's observing this wave-like property, right? So that eye is the eye of the observer. In this case, it could be a camera, right? That's trying to observe what's happening. And so what do we see there? No interference pattern, no wave-like property. So why is that happening? The process of observation, what does that mean? If I am observing something, an event related to light, I am observing a photon, right? So if I am observing a photon, if I am detecting a photon, then it essentially collapses this particle nature of light, rather it loses its wave nature of light, right? And then from that point onwards, it's actually just propagating as a particle. If I am observing, I am actually intercepting the photon. Okay. So, of course, you would ask that if I am intercepting the photon, then that photon cannot go past that slit, right. So, that's what is that. So, that particular photon is lost, it is already collapsed in that observation process. Okay. But the principle that is explained beyond that is that that photon might have collapsed, but other photons are coming up, right. But just the fact that you have an observation and that observation is loaded on one side, right. So, it is actually starting to disturb this wave function that corresponds to the photon, right. Once it's disturbed that wave function, then it cannot proceed further with a wave like property. Okay. So, then it just goes as some random particle that's bouncing around. Okay. So, of course, this is a fairly, like I said, advanced concept that I don't expect most of you to get right away, but nevertheless, I think the takeaway point from here is more of this, right. So, you can have emission of photons, okay, coming up, and this emission, if we go back and look at the case of an incandescent lamp, right, we know you heat up that filament, it emits photons, okay, and what Planck said was that is actually quantized particles, that is not just some wave that is generated, right, it is actually quantized particles that are emitted. And quite interestingly, depending upon the temperature of that black body, it can emit multiple colors of photons. Nu is not specific to one transition, you could have multiple transitions. If we go back and look at this picture that we have here, this could be multiple transitions, right. So, you could have multiple energy levels and you could have multiple transitions of different colors with different energies, right. So, that's what we were seeing there, and so that explains why an incandescent lamp looks yellowish, okay, but it has got yellow, orange, red spectral colors, a little bit of green also maybe, right. If you heat it up further, so we are not able to heat it up normal tungsten filament much more, we are not allowed to heat it up, but if you heat it up further, can you imagine what is happening? What color would it look like? Would it still remain yellow or would it be some other color? So, you would have maybe more number of colors, but would it look yellowish or would it look something else? So, what are you doing when you are heating up a material? You are building thermal energy, right. Thermal energy is quantified by kBT, where kB is the Boltzmann constant, right, multiplied by T. So, when you have higher temperatures, you have higher thermal energies, and because of that, what happens? You have building up of electrons at higher energy levels, okay, and due to which, what sort of photons do you emit? If my energy gap is really large, you can now have higher energy photons. Higher energy means higher frequency, and higher frequency means what in wavelength? Shorter wavelength. So, if it is yellowish, at a particular temperature. If I increase the temperature, what is it going to look like? Closer towards the blue, right? Maybe it will start looking greenish and then bluish and so on, right? So that's what we are talking about here. So key thing is, Einstein actually took something that Planck had done and then applied it to some other long-standing problem, and then said, light consists of photons. Okay, so light can be characterized, light propagation can be characterized as as propagation of these particles known as photons. But the key thing that we realized through this just this video that we saw, what does it show? It basically says light or these photons exhibit wave particle duality. Right? So it can be characterized from the emission perspective. It can be characterized as emission between two energy levels, right? And so emission of quantized electromagnetic wave packet, which we are calling as a photon, but that photon has wave-like properties just because that electromagnetic fields that correspond to that photon are extending in the transverse direction. Okay. So with this sort of a picture, let's now see what should be the properties of the photon. Okay. So let's go ahead and try to look at this in a little more detail. So we said E equals to h nu. So to really understand what this means, let's actually draw the electromagnetic spectrum and see how energy, frequency and wavelength, because if E is equal to h nu, this can be written as hc over lambda, right, where c is the velocity of light in vacuum, right, and if conversely, if you are trying to find value of wavelength in say in micrometers, lambda can be written as, since h and c are constants, h corresponds to a value of 6.63 into 10 power minus 34 joule seconds, and c corresponds to 3 into 10 power 8 approximately 3 into 10 power 8 meters per second. The actual value is 2.99998 something, okay, but we approximated 3 into 10 power 8. So since those are constants, lambda can be expressed as 1.24 over the energy, when the energy is expressed in electron volts. Okay. So as far as the Planck's constant is concerned, we are using a unit of joule seconds. So where clearly the energy is expressed in terms of joules, and here we are expressing energy in electron volts. So what does 1 electron volt correspond to? 1.602 in 10 power minus 19 joules, right. So just make sure you are comfortable with these different units. Okay, so let's look at how what these correspond to. Let's say this is nu, it's in frequency in hertz. So, we are going from 10 power 15 to 10 power 14, 10 power 13, 10 power 12, power 11, power 10, 10 power 9. 10 power 9 is what we typically deal with, right? What is happening around 10 power 9 hertz? Around a gigahertz? Your mobile communication, right? That has a carrier frequency of 10 power 9 hertz, but we are expanding the scale all the way to 10 power 15. And let us actually also represent the wavelength lambda, right. So, this corresponds to, it's 0.1 micron or 100 nanometers, and somewhere over here it's 1 micron, here is 10 micron, 100, and then we get to the millimeter waves, 1 millimeter, 10 millimeter and 100 millimeter. And then if we look at energy scale, of course that is also going this way, that's E expressed in electron volts. So, 10 power 15 would correspond to about or 1, actually the scale is like this, 1 micron, let us say, is our reference. 1 micron corresponds to roughly about 1 electron volt, right. So, if lambda equal to 1 micron, then that corresponds to 1.24 electron volt. So, 1 is somewhere over here. So, this is going towards 10 electron volt and so on. So, 1, and then this is 0.1, this is 0.01, this corresponds to 0.001 and so on, right. So, in energy we are going down in energy as we go down in terms of frequency, clearly, right. So, to give you a feel for what we are dealing with normally, we have basically blue happening over here and red happening over here. So, blue wavelength around 0.45 or less than 0.5 microns, and red greater than 0.6 microns. Okay. So, the visible region happens over here, and in the visible region the corresponding frequency is in the order of 10 power 15 hertz or hundreds of terahertz, and the corresponding energy is going towards, as we go to ultraviolet region, you have higher and higher energy, lower wavelength, but higher energy. So, it is not surprising that when in the photoelectric effect was first looked upon, they used ultraviolet radiation and they were able to see these electrons coming off, right. So, clearly that radiation corresponds to fairly high energy. Okay. So, we understand photon energy. Okay. So, while we look at it, what about photon momentum? What about photon mass? Does the photon have a mass associated with this? It is an electromagnetic wave, okay, so photons have 0 rest mass. So you cannot like catch a photon and weigh it, right. So photons have 0 rest mass, but it does carry momentum. So when we look at photon momentum, so that is going to be is given by energy over c, which can be written as h over lambda, and that can be written as h cross multiplied by k, right. K is a wave vector 2 pi wave number 2 pi over lambda, and h cross is nothing but h over 2 pi, right. So photons have 0 rest mass, but it can carry momentum. In other words, if a bunch of photons are illuminating a surface, you could have certain energy imparted on the surface, okay. So that is what we call as radiation pressure. We won't go into the details right now, but basic point is that the photon can carry momentum. We will come back and qualify this in a little more detail in a few minutes, but let's just move on with this picture for now, okay. And then there is this question of probability of finding a photon. So we say that photons can be emitted at different time scales, at different directions, and so on. So what is the probability of finding a photon? So photon probability is such that if you say probability of finding a photon at a particular location r, right. So P of r over some unit area, right, is actually proportional to the intensity of light in that location, okay. So essentially it says that if you have higher intensity, then there is a higher probability of finding a photon there. So let me just explain that. Insert a new page, okay. So let's just look at this. So in our previous lecture, we looked at Gaussian beams, right. So you have a laser, right, which is emitting let us say plane waves, and we said when we look at the intensity in the transverse direction, that is the transverse plane transverse to the direction of propagation, that intensity was for a perfect light source with only the fundamental transverse mode operating. So that would have looked like a Gaussian function, right. Now in terms of photon probabilities, what are we saying? We are saying that if the intensity is high, then this corresponds to a high probability of finding a photon, and similarly this region represents a low probability of finding a photon. Okay. So, that actually explains some of the randomness associated with light. Now, we are starting to talk about finding a photon in terms of probabilities. Okay. So, the classical measure of light has been the light intensity. So, now what we are saying is, based on that measure, if you look at the photons, we will find that there is certain regions where there is larger intensity of light, you have better probability of finding a photon. And if you extend that to something that we did earlier into a Young's double slit experiment, and we said, okay, the Young's double slit experiment, what we expect to see in the far field is some intensity pattern like this of constructive and destructive interference over there. And what we are saying here is this high intensity, if you say that the intensity is increasing this way manner, here we have a high probability of finding a photon, okay, and similarly this is indicative of low probability of finding a photon, right. So, that actually reverts back to this picture over here. So, clearly we see that in this picture you have certain regions where you can the photons are denser, when you have a large number of observations. Of course, if you make many more number of observations, you will find that these bands are very nicely formed, but that just corresponds to the fact that you have high probability of finding a photon, you have low probability of finding a photon in other areas, and it's not like there is zero probability, right. So, you always say high and low, but you could always find one of these photons showing up in the so called dark band. So, unless it is absolute zero intensity, you cannot rule out the probability of finding a photon there. So, the question is, the total probability, does it correspond to 1? So, we will just go back and look at the issue of what you already experienced previously, which is a 50-50 beam splitter. So, 50% of the light goes here, 50% of the light goes here, and what we are saying is, in terms of photon probabilities, if you have one photon, 50%, we are not splitting a photon, by the way, okay, it has got 50% probability of going one way and 50% the other way, right. So, what that means is, if you have multiple observations, you will find 50% of the photons have ended up there, 50% of the other 50% has ended up here. So, the question is, if the total intensity is, so first of all we are saying that probability is proportional to that intensity. If the total intensity is not conserved, is the photon probability conserved? Actually, that is a hypothetical situation, because the intensity, if you have a certain intensity, you either have reflection, refraction, scattering, absorption, but you have to account for all that intensity, right. So, as long as energy is conserved, we are saying, okay, the photon probabilities need to be adding up to 1. right. So, we are not introducing anything new here. Okay. So in terms of finding a photon, we are saying that it's a probabilistic event, and from that perspective, this actually leads to this other principle, which is called photon uncertainty. Okay. Just like in quantum mechanics, you have an uncertainty principle. What is the uncertainty principle? Heisenberg uncertainty principle, which states that the error, the uncertainty in finding the momentum multiplied by the uncertainty in finding the position is at least h bar over 2, right. So, similarly, the photons have an uncertainty associated with them, that is the RMS error, the root mean square error in finding an energy of the photon multiplied by the RMS error in determining the time at which a photon is there at a particular point, that is got to be greater than h bar, h cross over 2, h cross is basically h over 2 pi, right. So, what does this mean? What is the implication of this? And this is something that we have already in certain ways seen also. Okay. So, what does this photon uncertainty mean? Let's take the example of a single frequency, so monochromatic source. Okay. So, you have if you have a monochromatic source, well, I should call this nu, right. So, it is a single frequency source. So, if there is something called a single frequency source, the uncertainty associated with determining that frequency goes to 0. Okay. But in time, what does this represent? When can you tell through observation in time that you have a monochromatic source? If you are observing it with time. So, if it is characterized by a periodic waveform, then you say that's monochromatic. But to absolutely say this source is monochromatic at all times, you essentially have to make an infinite observation. In this case, unless you can go to an infinite observation, you cannot characterize this as a monochromatic source, right. So, if your uncertainty in frequency goes to 0, the uncertainty in time goes to infinity. Okay. So, that is what we are talking about as far as the photon uncertainty is concerned. Of course, you can play it the other way also. You could have a source which actually exhibits polychromatism, and then you essentially take a sample of that and you look at it in frequency space, you would find that it has got multiple frequencies, okay, which is something that we already saw from perspective of this Wiener-Khinchin theorem. We were saying that we were saying it more in terms of the power spectral density and autocorrelation, but here what we are saying is for a polychromatic source, if you take a sample of that wavefront and look at it in a sample of that wave in time, and we look at the frequency content, it will have multiple frequency content, right. So, this photon uncertainty is once again saying that, okay, what we are dealing with is a quantum particle, right. So, it exhibits all these quantum natures that you associate as we have seen in quantum mechanics, okay. But here we are talking more in terms of energy and time determination, okay, where of course energy is related to frequency. So, it is basically frequency and time relationship is what we are looking at. Talking of time, I think we run out of time now. So, let us stop here and we will continue from this in the next lecture.